Yesterday I forgot to mention that this two terms epsilon I and epsilon q should be Gaussian distributed with zero mean. Okay, when is this zero mean? If they are not zero mean, then we will not get Rayleigh distribution. Okay. The next example that we'll consider is the exponential distribution. Or exponential PDF. So it has an exponential function. Again, it is defined only for positive values of x, and mu should be greater than 0. Okay. So it goes like this. Now, where do we use the exponential PDF? In waiting time problems. To model the waiting time for an event to occur. We use the exponential PDF or exponential distribution. For example, suppose you have gone to bank and you are waiting for the customer service person to attend to you. So how long do you have to wait until he or she serves you? So that waiting time can be modeled as an exponential distribution. Then to model the lifetime or survival time of a system or any living being. We use the exponential distribution. So as time elapses, the chances of survival diminish. So a good distribution to model this is the exponential distribution. Okay. The third one is, and the last one for continuous random variable, is uniform PDF. Now we often use this PDF when we have no information, no knowledge about the particular thing. Okay, so suppose you are expecting an important telephone call, okay, but you do not know when exactly it will come. You know that it will come sometime between 9 a.m. and 5 p.m. But the exact time is not known. So the time at which the telephone call would come can be uniformly distributed. Uniform distribution means, so everywhere within the domain, it has the same value. The PDF has the same value. Let's say this is A, this is B. This has to be B minus A because the area under this must be unity. So the magnitude has to be B minus A. So we often use the uniform distribution when we have no prior knowledge. Okay. Even in signal processing, suppose we are trying to estimate a parameter. It's a deterministic parameter. We know that it has a particular value. It's not random. But we have absolutely no information about the range of values in which it will lie. So based on the measurements, we want to estimate the parameter, but we have no prior information available. So in that context, we use uniform distribution, uniform PDF as prior information uh, mm, of the quantity that we want to estimate. We may somewhat know the range of values, but we have no idea which particular value is more likely. Then we can use the uniform distribution to model this parameter initially. So when we look at different algorithms, we see that we can incorporate some prior knowledge or prior information in the form of a distribution. In fact, we are going to do a simple problem today. There also you will see that this prior information is incorporated as a prior distribution. Okay, there is a particular name for that. When we have no information about which value is more likely, we just use the uniform PDF as the prior distribution. Okay. So that's all about the continuous random variables. We looked at 4 examples: Gaussian, Rayleigh, yeah, exponential and uniform PDFs. And later we'll discuss a theorem which justifies why the Gaussian PDF is more likely or most common one. Okay. But before that, let's see some examples of the discrete random variables as well. Okay, the first one that we'll consider is called Bernoulli trial. So a Bernoulli trial is a random experiment with 2 possible outcomes. So any random experiment with 2 possible outcomes can be described as a Bernoulli trial. Okay. So let's say the value corresponding to the first outcome is 0 and for the other one is 1. So we are interested in knowing the probability that x is equal to 0 and the probability that x is equal to 1. So let's say this one is q and then this has to be 1 minus q, right? So this is called a Bernoulli trial. Next one is binomial distribution. So if we perform the random experiment with 2 possible outcomes n number of times, so each time we'll have one of the 2 possible outcomes, right? So what is the probability that a particular outcome will appear or occur k times out of n experiments? So that probability has a binomial distribution. So we have N, C, K possible combinations, right? And let's say we are interested in x is equal to 0 and the corresponding probability is Q. So Q occurs K times, and then 1 minus Q must have occurred N minus K times. So this is the probability that that particular outcome occurs K times out of N experiments. This is the probability of the binomial distribution. So K can take any values. 1, 2, and so on. In fact, we can use 0 also. The third one and the last one is the Poisson distribution. Here we are interested in the probability mass function. And since this is a discrete random variable, it takes on discrete values. Okay. Here is this is the average value. Now, when do we use the Poisson distribution? To model a given number of events that can occur over a given time interval. We use the Poisson distribution. Now, we can use this distribution provided the event is occurring at a fixed rate. Okay. And independently of the last occurrence. So only if these two conditions are satisfied, that the event is taking place at a fixed rate and it is independent of its last occurrence, we can use the Poisson distribution to model the number of times it occurs over a given interval. For example, suppose a river overflows on average once in 100 years. Okay. So the average value here is 1. A is equal to 1. It overflows once in 100 years on average. Now we want to know what is the probability that it will overflow two times, twice, thrice, and so on in the same 100 years period. So for that, we can use the Partian distribution. So if you want to know the probability that it overflows twice in 100 years, then we have to use k is equal to 2 and then a is equal to 1 because it overflows once in 100 years on average. So a is equal to 1. So if you use k is equal to 2 in this, we will get the probability that it overflows twice in 100 years. Now keep in mind that the period cannot be changed. The time period of interest cannot be changed. If A is for 100 years, then you can get different values for the same time interval, okay, time period. So these are different examples of discrete and continuous random variables, and I hope this gives you some ideas that they are not completely abstract. They have physical significance. We can use these distributions to model the behaviors of physical systems, right? Next, quickly look at the theorem that justifies why the Gaussian PDF is the most common one. So it's called the central limit theorem. Okay. So it states that the sum of a large number of mutually independent random variables when I say mutually independent, it means just like mutually independent events. So occurrence of one does not affect the other. So if one random variable takes on a particular value, you cannot predict what the other random variable will take. Then we call them independent. Later we will quantify this with the help of, in fact, soon after this we will look at that, how we can mathematically represent two independent random variables. Two mutually independent random variables with 0 means. So they should all have 0 means and finite variances. We defined means and variances, mean and variance yesterday. With 0 means and finite variances tends to have a Gaussian distribution. If now you cannot pick any random variables, okay, you also need to satisfy some criteria. If the individual variances, so let's say this is the variance of the ith random variable. If the individual variances are much smaller than their sum, okay, for all I. What is sigma? Sigma is the sum of all. Capital sigma is the sum of all small sigmas. Okay, only if this condition is satisfied, meaning none of the random variables dominate over the others. Okay, So all have similar variances, and 0 means, and we need to consider a large number of random variables, mutually independent random variables. Only if all these conditions are satisfied, their sum tends to have a Gaussian distribution. Okay, now the notation that we are going to follow in this class for Gaussian distribution is this. So, in another name of the Gaussian distribution is normal. We use italicized N, Gaussian or normal. In the first entry within parentheses is the mean, and the second one is variance. Okay, so this is the convention we are going to follow in this class, and this is a standard convention for representing the Gaussian distribution. Okay, now let's express the theorem mathematically. So let's say we have n number of mutually independent random variables, where I is from 1 to n, and n is very high. Okay, now each random variable has 0 mean, and the corresponding variance is sigma I square. Then the sum is over all I. Okay. Now we calculate the sum of the individual random variables. So let's call that as now we go one step forward and sum this. So each random variable is divided by its corresponding standard deviation, and then only they are summed from I equal to 1 to n. Okay. Then it can be shown that when n is large, and this condition is also noted, the sum tends to have this distribution. So the resulting distribution of the sum as n becomes large tends to have 0 mean and unit standard deviation or unit variance. Okay, so this is also called standard. The normal distribution or the Gaussian distribution with 0 mean and unit variance is also called the standard normal PDF. Okay, we often use these two terms PDF and distribution interchangeably. Okay, there is nothing wrong with that. Generally, when we say distribution, when describing things, we mean the PDF. Okay, it's not the CDF. If we are referring to CDF, we specifically mention CDF, cumulative distribution function. But in general, when we say distribution, we usually refer to the PDF. Okay, the probability density function. Any question? No question? You understood the central limit theorem? Yes or no? So if there is
Yes, ma'am.
okay. So far we have considered a single random variable. Now let's extend this concept to two random variables. Later we'll extend that further to n-dimensional random variables. Okay, so let's first consider two random variables, how to deal with or how to handle two random variables together mathematically. So just like joint events, here we will have joint distributions and joint densities, joint CDF and joint PDFs. So let's say x and y are two random variables. Okay, now when we handle two random variables, we are naturally interested in finding the joint distribution, joint PDF, joint CDF, just like joint probability, right? So let's start with the joint CDF. So we have capital F, and here in the subscript we now need to put both the random variable notations x and y, and then within parentheses we have their values. So this is the joint probability that capital X is less than equal to small x and capital Y is less than equal to small y. Now we know that this is an event, this is also an event, right? This is how they are related to the physical world. So basically we are seeing the joint probability of two events. So this is an event, this is another event, and then we have put the intersection. So actually by the joint CDF, we calculate the joint probability of two events. So this is the joint CDF. Okay. Now similarly we should have a joint PDF, correct? Now yesterday we derived the PDF from the CDF, right? We considered the differential CDF and then from there we derived the PDF, correct? Now for this we need to do the same in two dimensions. Now how do we visualize this or this? So earlier we plotted only along x. Now we have another variable, right? Y. So basically we required three dimensions. So this is x, along this the domain of x changes. This is y, along this the domain of y changes. So basically instead of having a line, now we have an area, x and y plane, right? And then along the z, we either plot capital F or small f. So this is how we need to visualize. So now we actually have a surface function. So whether it is joint PDF or joint CDF, you need to find its value for given x and y. So basically we have some sort of a surface along the z direction. Okay, now let's find this one. How we can find the joint PDF from the joint CDF? Let's do that derivation quickly. For that, let's draw the x and y plane. So let's say this is x, this is y, and we take our rectangular area. So at this point we have x and y. Here we have, so its width along the x direction is, let's say, delta x, and along the y direction it is delta y. So this is x plus delta x and y. The y dimension has not changed. This point is x plus delta x and then y plus delta y. And then this one is x and then y plus delta y. So we have this rectangular area, and let's find if x plus delta x and y plus delta y. Now we know that if I am dropping the subscript for simplicity of notation, we know that this is how we define the joint CDF. Right? So let's first find the expression of this one. So if we consider this area, this the corresponding probability is that the probability x is between x small x and x plus delta x, and y this one, right? Next, let's find the probability for this one, for this blue shaded area. So here x is varying from x to x plus delta x and y is constant, right? So let's write the corresponding probability. So it is P y is not changed. How about this one? This yellow area? What can we write for this yellow area? What can we write for the yellow area? Huh? What can we write for the yellow area? So you understood how I wrote the probability for the white and blue areas? Did you understand that or not?
Yes, ma'am.
Yes, ma'am.
Okay, then can you tell me what we should write for the yellow area?
P of 0 less than or equal to x comma y.
Then in terms of capital F, what can we write?
Ma'am, f of x comma y.
Yes. Then who will tell me what should we write for the red area? Somebody else. What can we write for the red area? Tell me in terms of the probability. Who else is there?
P of 0 less than x and y plus delta y.
Right. Now, our objective is actually to find this term, the first term on the right side, in terms of f's, okay, this capital F function. So we already have this f here, so this we can take on the left side. We have an f on the left side. So all we need to do is to express these two probabilities in terms of f, right, using f. Now here you see this is the probability that capital X is within x and x plus delta x, and capital Y does not change, right, along this direction. So how can we express this term? If you can do this, the same we can do for this probability also. So how can we express this term? Okay, when I write y, it means actually function will write on y. So what can we do with this probability so that we can express this in terms of f? I'm giving you a hint, we need to subtract two f functions. So what are they? Can anybody tell me which two functions we should consider? The answer lies in this, because this is different. So we need to divide this into two f functions.
Ma'am,
Yes.
ma'am, f x plus del x comma y minus fxy.
Yes. Now similarly for this also we can write f right. Now we have two of this and there's a negative sign before them, right? Here we have one f. So one of them will cancel out and we'll have negative f of x and y, right? Now let's take all of these f terms on the left side, then we will have an expression of this one. On the left, we already had x plus delta x and y plus delta y. And then we need to take this one on the left side and this one also on the left side. So we have negative and then this negative f of x and y will also come. So that will become positive. Okay. Now let's concentrate on this term. So this is the probability that x is between small x and small x plus delta x, y is between small y and y plus delta y. Now when we consider a single dimension, uh, we wrote that this is equal to fx dx or under delta x, not dx, because we have used delta x on the left side, so we should write delta x, right? So this is what we wrote for the single dimension, right? Now here we have two dimensions, correct? So let's write this probability as follows: fxy. So this is the joint PDF. Fxy is the joint PDF of x and y, and we multiply delta x for the single dimension. Now we have two dimensions, so we need to multiply delta x and delta y, right? And then we have this whole thing on the right side, right? That whole thing, I'm not writing that again, on the right side. Then we take delta x and delta y on the right side and let them go to 0. We have this one on in the numerator. Now this is actually the fundamental definition of the second derivative. We have del square x. Okay, so whatever expression we get, final expression we get by putting this whole thing in the numerator, dividing that by delta x and delta y and letting delta x and delta y go to 0, we actually have the fundamental definition of the second derivative. So this shows that the joint PDF is the second order derivative of the joint CDF. So in case of a single random variable, we found that it is the first order derivative of the CDF. In case of the joint PDF, we have second order derivative of the CDF. Okay. Now how about the case when x and y are independent? X and y are independent. So let's start with the CDF. We know fxy, x comma y is actually the joint probability that x is less than equal to small x and y is less than equal to small y, right? Now we know x and y are two independent random variables. So this event and this event, they are actually independent. So we have the joint probability of two independent events, correct? And we know that for two independent events, the joint probability is the product of individual probability. So we have this one. Right? And we know that this is the CDF of x. You can write fx. And this is the second term is the CDF of y. Right? So for two independent random variables, we have the same result as the joint probability. Thus, joint CDF is the product of individual CDF. How about the PDF? So you just put this in the second order derivative and you will find straight away that PDF also has the same relation. It is the product of individual PDFs. Now this is true only when x and y are two independent random variables. Okay. Uh, what if they are not independent and you have been given this one joint PDF? How will you find the individual PDFs? And how will you find the joint CDF? So the joint if you want to find the joint CDF from the PDF, you just need to do double integration. Earlier we did single integration, now we need to do double integration. So this will give you the CDF, joint CDF from the joint PDF. How about the marginal or the individual PDFs? So individual PDF, they are called marginal PDFs, okay? It is also possible to find the marginal PDFs from the joint. How? You just need to integrate along one dimension. So if we do this, we are actually eliminating x. We are integrating it from minus infinity to plus infinity, and this will give us the marginal PDF of y. So this becomes a function of y, and that is actually the marginal PDF of y. Similarly, if you integrate it with respect to y from minus infinity to plus infinity, you will get the marginal PDF of x. So using the joint PDF, we get everything. We can get marginal PDFs, we can find the joint CDF, and since we have the PDF, we can also calculate other parameters. Now in this context, note that the PDF actually holds everything, all the information about the random variable. So whether you are considering a single random variable or multiple random variables together, if you have the joint PDF, so when you are considering multiple random variables, if you have the joint PDF, you get all the information about both random variables. You can extract the information about individual random variables because you get the marginal PDF. You can find joint CDF, you can do everything. So a PDF has all information about a random variable. So when you consider multiple, you need to consider joint PDF. Now we can. Why do I say this? Because we can calculate CDF. We can calculate the CDF. We have seen how to do this for one dimension. We have extended that to two dimensions, and it can be done for higher dimensions as well. The only thing is that you need to do higher order integrations. Then we can also calculate mean, variance, etc. Okay. We can calculate higher order moments also. Now, another advantage of PDF is that it is intuitive. What do I mean by this? See, suppose we have, let's consider a single dimension because it is easy to visualize. So let's say this is the PDF of the variable, and this is capital X. Now we just take two values of X. This is, let's say, x1, and let's say this one is x2. And then we consider an elementary rectangular strip adjacent to it at x1 and this one also at x2. And then we calculate the area of the rectangular strips. So each of with delta x. Now we can see clearly that this area, the rectangular strip on the left, has a higher area than the rectangular strip on the right? Now we also know that the area of the strip is actually the probability that capital X is in that region, correct? So this area tells us the probability that capital X is in this region. Similarly, this area tells us the probability that capital X is in this region. And since this area is larger, we can quickly say that X is more likely to be in this region than in this region. So just by seeing the PDF, we can quickly say in which region X is more likely to be. This is why we say that it is intuitive. It also allows us to visualize quickly in which region X is more likely to occur. Now we can get this information from the CDF also, but it is not as evident as the PDF. So in case of the CDF, it goes like this. We need to look at the slope, in which region the slope is steeper. That is a little difficult to find out. This one actually tells this information quickly. So the PDF actually contains all the information about a random variable. Okay. So if we know the PDF of a random variable, we know everything about the random variable. But unfortunately, it is most of the time it is not possible. In case of, especially in the case of multiple random variables, it is not possible to know the joint PDF. Okay. And then what we need to do is to get this mean, variance, etc., so that we get as much information as possible. Okay. Next, I'll quickly tell you about the conditional. I'll not do any derivation here because we are running out of time. I don't think I'll be able to do that derivation, so I'll just give you the expression. Now, just like conditional probabilities, we also have conditional uh, densities and distributions. Conditional PDF and CDF. So what is the conditional CDF? Conditional CDF has this notation: X given Y. In case of conditional probability, we saw that A given B, right? Similarly, here also we have X given Y, and then in the argument also we write X given Y, and this is actually the probability that X is less than small x given Y is equal to Y. Now you may ask, how about a conditional random variable? What will happen if the y is a continuous random variable? Then the probability that it takes on a particular value is 0. So to deal with that, this we can write as follows. We take a small delta y, let it go to 0, and then this. Okay, so when we have a continuous random variable in y, we can think of it as this way. So this is the conditional CDF, and then it can be shown that the conditional PDF x given y follows the same uh, relation as the conditional probability and joint probability. It can be proved, but I will skip the proof. I will not do it. We don't have time for that. We need to discuss other things today. But this can be proved. Okay. Now see, this is actually what we get in Bayes rule also, right? Using Bayes theorem also for conditional probability, the same equation is used, right? We have the same equation there also. So to get the conditional PDF, we need the joint PDF and divide it by the marginal PDF. So if we are conditioning x on y, then we need to divide the joint PDF by the marginal PDF or individual PDF of y. Okay. So this is called x given y. It is also called x conditioned on y. Okay. Now in estimation theory, filtering and estimation, this conditional PDF is very important. This will be clear to you in a while when we discuss an example. Now using the conditional PDF and CDF, we can also calculate the conditional mean and variance. We use the expectation operator, x given y. To find this, we need to integrate it from minus infinity to plus infinity. And since we are operating it on x, x has to be used inside the integration. Now since this is a conditional mean, we need to use the conditional probability, dx. Okay. Then for the conditional variance, the same thing has to be done for variance. Given y, actually we need to do everything with the conditional PDF. Whatever we did for a given random variable to calculate the mean and variance, we are doing that, but with the conditional PDF. Okay. Now notice carefully. Here what we are doing? We are actually integrating x out. Now here we do not have x. This is actually a function of y. While doing this integration, we assume that y is given. We treated y as a deterministic quantity. We did the integration with respect to x. We varied only x. After the integration, we basically get a function of y. The same holds for the conditional variance also. But y is also a random variable. So this is actually a random variable. It's a function of y, which is a random variable. A function of a random variable is also a random variable. So this is a function of a random variable. So this actually is a random variable. This is also a random variable. Now, in this context, I have an exercise for you. You need to show that expectation of x given y is the expectation of x. So in this case, you are actually using the conditional PDF. Now, based on what I said, you need to find which PDF you will use here. Okay. I said that this is a function of y, so you should decide which PDF you want to use. And for this one, you need to use the PDF of x. Is the question clear to you? Do you understand what you need to prove? Yes or no? Did you follow whatever we discussed regarding conditional densities and conditional CDF, PDF and CDF?
Yes, ma'am.
If you do not understand, ask me, okay? Do not keep quiet, because if you do not understand, even if questions are asked, you will not be able to answer anything. By the way, the syllabus for the second test is attitude and filtering and estimation. So whatever we discussed till 23rd will be included. So basically, I think uh, most of filtering and estimation and attitude both are included in the second test. If we solve some problems on 24th based on what we discussed till 23rd, that is also included. So, and you have 20 marks for the test. So if you do not understand anything about this topic, ask me. Otherwise, you will find it difficult to follow. Okay. Let's take a 5-minute break. We will be back at 12:17. Okay. Um, now we discussed that using the delta functions we can have a PDF even for a discrete random variable, right? So whatever we discussed with respect to joint distribution, joint CDF and PDF can be done for both continuous and discrete random variables. For the discrete random variable, either we can use the PDF form using delta functions, or we can have PMF, probability mass function. If we are using the probability mass function for the discrete random variable, then instead of integration, we need to do summation. Okay, so then everything has to be handled in a discrete sense. If you are using the PMF for a discrete random variable. If you are using the PDF for a discrete random variable using the delta functions, then integration and whatever we discussed can be done even for discrete random. And then, okay, uh, here I'll note how to get the conditional CDF from the conditional PDF. The same thing has to be done. The moment we do X conditioned on Y, we do not treat Y as a random variable. The moment Y appears on the right side of the bar, Y is not random. X is the only random quantity. Okay. So to find the conditional CDF, you need to do the integration from minus infinity to X and use the conditional PDF. So this will give you the conditional CDF from the conditional PDF. Okay. Now in estimation, the conditional PDF mean and variance, these are very important. Let's understand this with the help of a simple example. Suppose S is a random variable. That we want to estimate. Okay. And to estimate, we know that we need some measurements, right? Let's say we make measurements of S as so y is the measurement of S, and when we make some measurements, noise gets added. Okay? So n now we can model as a random variable. Okay, now both S and N are random variable, but the difference is that S is what we want to estimate, N is what we want to reject. So N is not desirable, it's a nuisance for us, but we can't avoid it. Whenever we make measurements, some noise will always be added. We can't help it. It's a nuisance for us. S is also a random variable, but we want to extract S from Y. We are actually looking for S. So both are random variables, one is desirable, another one is a nuisance. Now since S and N are generated by two completely different processes, they are also independent. So S and N are independent. Okay, they are independent. And let's assume that they are Gaussian. Both S and N are Gaussian distributed. Okay. Now, since they are two independent random variables, we can apply the formula for uh, mm, the joint PDF is the product of individual PDF. So I'm just dropping the subscript because it makes things a little clumsy. Uh, so this is the joint PDF, and we can write this as the product of individual or marginal PDFs. Since S and N are independent, the joint PDF is given by the product of the marginal PDFs. Now let's assume that N is distributed as, so this is the notation we use to show the distribution. So it is Gaussian distributed. Let's say it has 0 mean and variance sigma n square. Okay. Then S is what we want to estimate, but we have some prior knowledge about S, which is given by a prior distribution of S, which is again Gaussian distributed with some mean S bar and sigma S square. So this is called the prior distribution, prior information of S. Okay, so we know before proceeding further, we know that from some prior knowledge, we know that S is distributed as Gaussian, okay, and Gaussian distribution has 0 mean and variance sigma is square. Now, if we cannot make any measurements, then we will use this S bar as the estimate of S. We have this Gaussian PDF, correct? And we know that the mean is most likely because the peak occurs at the mean. So we pick the average representative value, the most likely value, which is S bar. If we do not have any other way to know anything about S, no way to make measurements and do estimation, then this is what we will conclude from the prior distribution. But we actually want to make measurements and refine our prior knowledge. That is why we are doing all this. Okay, so we have the prior distribution of S, and in also we have defined, and we know that the measurement Y is equal to S plus N. Now it can be shown that for Gaussian distributions, when S and N are independent, the PDF of Y, the marginal PDF of Y is again Gaussian. Okay, now since this has 0 mean, when S and N are independent, we can show that the mean of Y is actually the mean of S and mean of N. You can actually show it using the, so basically, I have not discussed that. It will be clear to you when we talk about n-dimensional random vectors. It will be clear to you. So you just note that the mean of Y when S and N are independent will be just the addition of the mean of S, so S bar, and mean of N is 0, so it's basically S bar, and the variance is the sum of sigma S square plus sigma N square. Now we cannot do this addition just like that if S and N are not independent. Only if S and N are independent, we can add them up. Otherwise, we cannot add this way. Okay. So our objective is to find S given y. We are making measurements of y, and we want to refine prior knowledge about s based on y. So we actually want to find the PDF of s given y. This is what we are looking for. Okay. Now, what is the PDF of y given s? What does it mean? So we are treating y as a random variable given s, meaning s is a deterministic quantity now. Now let's look at this equation. S is a given quantity, it's a deterministic quantity. With that information, we want to find this PDF. But this PDF is not the same as this one, because in this case, we do not assume that S is given. S is a deterministic quantity. In this case, both S and N are random and they are independent. Whereas in this case, for a given S, we are interested in finding the PDF. So it's like we know that some event B has occurred, and then we are interested in finding the probability. It's the same thing actually we are doing here in the form of the PDF. So what can we say about the PDF? Now since this is a deterministic quantity, it will not have any contribution to the PDF. It is deterministic, it is known, it can be assumed to be known. The only random variable here is actually n. Now the advantage is that S and N are independent. So whatever S is, N does not bother about that. N takes on values independently of S. So N is still the same random variable. S is a given quantity now, but N is the same random variable as before. So N can take on any value as per this distribution. Okay. Now here see what is the mean? Mean was S bar because we treated both S and N as random. But here we treat S as given. So when we are finding the distribution, this will also be Gaussian. Okay. When we are finding the distribution, S is given. Because this is a deterministic quantity, it will be the average value. So the average is S. Note the difference between this one and this one. Here it is S bar, here it is S, because S is treated as a given quantity. The S value may not be the same as S bar. Okay. How about the variance? The variance will come only from that portion which is random. We know that the only random variable now here is N, correct? So the variance is determined only by N, and we know that variance of N is this one. So the second entry will be sigma n square. So the PDF of y given S is Gaussian distributed. Its mean is S. Now why is it Gaussian distributed? You may ask why you use the Gaussian distribution, because N is the only random variable, right? Which is Gaussian, so we need to have a Gaussian distribution. And in fact, it has the same variance as that of N. The only difference is that it does not have zero mean because of S. S is the deterministic quantity, and any deterministic quantity will contribute to the average value, the mean value, right? So this is why I use the Gaussian distribution with mean S and variance sigma n square. Now how about this one? We are actually interested in this one. F of S given y. So can we do this one? What do you think? If I do this one and then proceed the same way as before, will it be correct? So earlier what we did, for this one what we did, we used y is equal to s plus n. S and n are independent. So whatever the value of s is, n is not affected. N is the same random variable as before, and therefore we can write this one because n is not affected. S is just deterministic. But in this case, S is not deterministic. For a given y, we are interested in finding the PDF of S. So can we proceed the same way as before? Yes or no? I'm just giving you 1 to 2 minutes time to think about it. Quickly tell me whether we can do it this way or not. And justify why you think so. If you think it is possible, tell me how it is possible. If you do not think it is possible, tell me why we cannot use the same approach as before. Just think of whatever I said for this one, whatever conditions I imposed, assumptions I made. I didn't make any assumptions, I imposed some conditions. So whether those conditions are valid in this context or not. Just think about that and let me know in a minute or two. So what do you think? Can we do it or not? I want some response from someone. Whoever wants to respond can respond. Since we need to discuss other topics also, please respond as soon as. If you do not know what to be done, say that also clearly. Can anybody respond and tell me whether this is possible or not?
Ma'am, y and n are not independent, so I think we
Exactly.
cannot.
Exactly. Y and N are not independent. Very good. See, S and N were independent. So whatever value S takes, N is not affected by that. But the moment we say that Y is given, we cannot say that N can take on any value. No, that is not possible because Y and N are not independent. So we cannot follow this approach for this one. So do you understand why it is not possible? This is not possible because y and n are not independent. So given y, you cannot say n can take any value. You cannot say that y is deterministic, n is the only random variable, so we can follow the previous approach. That's not possible. Y is given, meaning n cannot take any value. Okay? Then what is the alternative? What can we do? If you cannot do the same thing, can you quickly tell me what we can do? That answer also is with you only. Whatever I told you, based on that you can answer that question. What we can do? Just think of the relation that we talked about for conditional densities. So we know this one. We know this one also. We know this. We know this. How can we find this one? Who will tell me the answer? Hmm? Which formula will you use? We discussed this. Just before this one, we discussed this. When we are talking about the conditional densities, we discussed this. What will you do? Nobody can answer this question? Hmm? Which formula did we discuss in the context of conditional densities? Something we discussed, right, for conditional and joint densities? How we relate the conditional density with the joint density? Which formula did we discuss for that? To relate the conditional density to the joint density?
Ma'am, f x bar y is f x and y by f of y.
So can we make use of that? Why I am getting response only from Apur? Others are not following. How about others? Are you following or not? Are you following? Can you tell me whether you are following or not? Or I am
Yes,
going
ma'am.
too fast?
Yes.
So we can make use of that. How can we make use of that? What formula in this context? What should we do? To find this one, using this or whatever, you can use this, whatever you want. How will you make use of that? How will you make use of this one? What will you do? Hmm? What will you do? Okay, whoever wants to respond can respond. We do not have much time for this. So if somebody wants to respond, he or she can respond quickly. So you need the joint density. How will you get the joint density? Don't you have the joint density? Can't you find the joint density somehow? So to find this term, which two terms will you divide? Which two terms will you divide? Tell me first. So you want to find this one, right? S given Y. Now we need to divide two PDFs. So which two PDFs will you divide? You tell me. What will be in the numerator and what will be in the denominator?
Joint and y.
How will you find the joint density? How will you find the joint density? Don't you have the PDFs required to find the joint density?
F y bar s into fs.
Why bar? We have not used bar here. You mean this one? This one? Hmm? Which one you are talking about?
Yes, ma'am. Yes, ma'am.
Y, okay, Y, okay, that bar you are saying, okay, fine. Okay, Y given as, and then this one, f of y. So if y given, sorry, try this. So this one and then s of this one. So y given s and then f of s. We know this one, correct? We already talked about f of y. So f of y is known in the, we know this one. We derived this one we derived, and then we know f of s. So we know all the terms in the numerator and denominator. And we can find the conditional density of S given y. So I am giving you the final expression. If you want, you can derive it. It can be shown that it is Gaussian. Okay, now mu is nothing but the mean. Here I can introduce capital. Okay, so if you use the individual PDS in this equation and then do some algebraic manipulation, you can put this in this form. So this shows that it is again Gaussian distributed, and then from there you can extract the mean and the variance. So you know in the Gaussian distribution where the mean and variance appear, right? So from there you can find the mean and variance, and it can be shown that if you have done everything correctly, then you will get this one, these two expressions for mean and variance. Okay. Um, Now we are going to discuss some important points from this. This is actually, later we'll see that this is a kind of estimator, because we are estimating some quantity based on some measurements. Okay, this is actually an estimator, and this estimator is called minimum mean square error estimator. Okay, later we'll talk more about the minimum mean square error estimator, and you will find that the expression that we have got now is the same as what we get when you use the minimum mean square error criterion. Okay. Now, uh, note that here what we did, we started with some prior knowledge. We made a measurement. Using that measurement and prior knowledge and knowledge about the noise, we got this. We got the mean and the variance. Now suppose for this quantity, you have made multiple measurements. This is just one measurement. You have made multiple measurements. So with the first measurement, you start with the prior guess, okay, S bar, and then sigma S square. You start with this one, and this is also, assume that this is given. Using the first measurement, you get this and this. For the second measurement, what you need to do, you need to follow the same approach as before, but since you got a better knowledge, knowledge about the quantity, you will use these two as your priorities. So in the prior distribution, again assume Gaussian distribution, but this S bar will be replaced with what you have got here, and the sigma S square will be replaced with this one. So for the second measurement, you will use a better guess, which you got from the first measurement. And then for the third measurement, whatever refined estimates you got, you will use for the third measurement as the prior guess. So this way you can incorporate multiple measurements one at a time. And what is the estimate of S? Estimate of S is actually this one. This is the best you can do with the help of the measurements. So you say that based on the measurements, I get this estimate of S. Now as you keep on applying multiple measurements, if the measurements are proper, then your estimates will improve. The quality of estimates will improve. You will get better accuracy. This is one thing. Second thing, you just see we have sigma n square and sigma s square in the denominator, right? Now what if sigma n square is much greater than sigma s square? So this indicates that the quality of measurement is not good. So larger variance means quality of measurement is noise has a larger variance means the measurement quality is not good. Your prior knowledge is better than the measurements that you have made. Now the beauty of this estimator is that it automatically weights the two, measurement and prior case. So when sigma n square is large, automatically the first term becomes small and you give more weight on the second term. Now what happens when the measurement quality is good but prior knowledge is not so good? So in that case, sigma s square would be much larger than sigma n square. In that case, the reverse happens. It gives more importance to the measurement. It automatically gives less importance to the prior information. So it actually applies appropriate weights to measurements and prior information and gives you an estimate. Not all estimators do that. So this is an advantage of this kind of estimator, MMSE estimator, minimum mean square error estimator, and current filter also does the same thing. So it appropriately assigns weights between the measurements and prior information and gives an estimate. Okay. Now when both sigma n and sigma s are comparable, what will happen? It will give appropriate weights to both measurements and prior information. and this is in fact an advantage. Okay. Uh, what is the disadvantage? Disadvantage is that in this simple example we have the estimate as a linear function of y, but not all models will give a linear estimate of y. The estimate as a linear function of y. We actually, to the extent possible, we do not want to introduce non-linearity. But with the help of a minimum mean square error estimator, unless you have a simple model like this one, Gaussian distribution, there is no guarantee that you will get a linear function of y as your estimate. Okay? So this is a disadvantage of the estimate. So with this, I have explained to you how the conditional density plays an important role in estimation. And you also got some ideas about an important estimator called the minimum mean square error estimator. We have not derived the expression of that estimator, but when we derive that, and then I'll tell you more about it, we'll find that whatever we have got, the same expression can be derived using the minimum mean square error criterion. Okay, any question up to this? The disadvantage is that this is a non. It can give a non-linear estimate. What I mean by nonlinear estimate, it is the estimate is actually a nonlinear function of y. Okay, so we discussed two random variables x and y, right? We found the joint PDF, joint CDF. Now we can actually put these two random variables in a vector form. So let's denote that vector as x bar underneath, and this is basically a two-dimensional random vector x and y. And then if we extend this to n dimensions, we have n random variables, n elements. So we have x1, x2, xn. So basically n elements are there, and this is an n dimensional random vector. So first we discussed a single random variable that we extended to two random variables. Now from 2 we are going to n dimensions, and to deal with n dimensions actually we require a vector representation. Okay. Now if we want to find the mean of this, we just need to do this one. And then we need to find the individual means. We need to calculate the mean of each random variables. Okay. Now, for a single random variable, we define variance. For a random vector, we have covariance. It is a matrix covariance matrix, and we denote this notation. We will use this notation. So we have the expectation operator. So let's call this one mu bar. The same expression as before. Earlier for a single dimensional case we square this, but here we have a vector, so we need to do transpose. Okay. Now we can expand the terms within the third bracket. So then we have x transpose minus mu x transpose. We can take transpose inside, then this will be x transpose, this is the mu transpose. Then we have x mu transpose and then plus mu transpose. Now mu is a deterministic quantity. Mu is the mean of the random vector. So the expectation operator always operates on a random term. Okay. So we have E x transpose. Mu will come out because we need to operate the expectation of operator only on the random term. E x transpose is actually E of x transpose is actually mu transpose. Then similarly for the second term also we get mu transpose, and then we have plus mu transpose. So we basically have x transpose and then mu transpose. Now the first term is called correlation matrix. We denote this as R. I'll just give the expression of the correlation matrix and discuss the joint PDF and stop. The correlation matrix we got an additional term called correlation, which we did not have for the single dimension. Now correlation matrix E actually in this case has to operate on both x and x transpose. X means x1, x2, up to xn, okay? And then we have the transpose of that, right? So we have xn. Now if we multiply the individual terms, we basically have a matrix, right? So we have x1 square, and then we need to use this expectation operator on each of the matrix elements. If we do that, we have this one x1 square, then we have expectation of x1, x2, expectation of x1, xn, and then in this direction we have x, again x1, x2. So since x1 and x2 they are actually random variables, so it does not matter whether you put x2 first or x1 first. So in fact, if I follow the convention, I should put x2, but it does not matter, both are the same. x2, x1, so xn, x1, and the same here we have x2 square, so this will continue, and then finally we get xn square. So this is the correlation matrix. So what we did, we just took x transpose here, multiplied the individual elements, we got an n by n matrix, because each is of, so this is n cross 1 and this is 1 cross n. We get an n cross n matrix, and then we apply the expectation operator on each of the individual elements and find uh, the correlation matrix. Now, what is the joint PDF? Joint PDF is, earlier we considered the joint PDF of two variables, right? Fx, y, x comma y. Now we need to excuse me. Now we need to use n elements. So we have x1, x2, and then xn. So earlier we considered a two-dimensional case. We had joint PDF of x and y, and we had to use a three-dimensional plot to visualize it. In this case, actually we require n plus one dimension. So along n dimensions we have this each of these random variables, and then along the n plus one dimension we have the PDF. That is how we need to put it in the graph. But actually this is a scalar time. This is a joint PDF of x1 up to xn, and just say that this is the PDF of x bar. Okay, now how will you find this one? This we know. For this expectation operator, we'll just use the PDF of x1. For this one, to evaluate this one, we need to use the joint PDF of x1 and x2, because we need to apply the expectation operator, and we know the moment we have expectation operator, we need a PDF. Since we have two random variables x and y, it has to be a double integration, and the corresponding PDF has to be the joint PDF of the two random variables. So here we have need x1, x2, here we need x1 and xn, like that. Now, when we have the joint PDF of n random variables, it is possible to extract any joint PDFs. So we saw this in a two-dimensional case. We had the two-dimensional PDF. From there, we got marginal PDF. Similarly, from the n-dimensional case also, for the n-dimensional case also, we can extract PDFs of any subsets of random variables. Okay. I'll just give you the example of the joint PDF for a Gaussian random vector and stop. Okay, so for a Gaussian random vector, its part, the PDF is this. So it's basically the joint PDF of all n elements. So I'll not write that, it is already written on top. I'll give you the final expression. 2 pi. So if you write n is equal to 1, it will reduce to the expression that I had given earlier. K is the covariance matrix and mod K is its determinant. And then we have the exponential term. The exponential term has actually a scalar argument, minus half x. Earlier we had a square term, now we cannot do square. Mu is the mean of the random vector. We had variance in the denominator earlier. Now we need to do the inverse of the covariance. This one. Now see, this is n cross 1, and we are doing transpose, so it basically becomes 1 cross n. The whole thing is 1 cross n. This one is n cross n, and this one is again n cross 1. Right? So, let's write the dimension of the transpose. So this one is 1 cross n. So 1 cross n cross 1, n cross 1. We basically have, after multiplication, we have 1 cross 1. So we have a scalar pile, and the exponential function is to operate on the scalar pile. So this is the example of Gaussian distribution for an n-dimensional random vector. Okay, that's it for today. Any question? Okay, I have a homework problem. It is easy. A is a matrix, B is a vector. A and B are deterministic. To show that the mean of Y is given by this. Mu x is the mean of x, and the covariance of Y is A. Okay, so I gave one more exercise for two homework problems. Both are easy actually. None of them are difficult. So that's all. Do you have any questions? If you are not following something, ask me after class. Otherwise, you will not be able to answer questions in the exam.